You live on a planet that's 4.5 billion years old, and your industrial civilization is barely 200, and yet you just assume you're the first ones to ever do this. How safe is that assumption, really? In this video, we're going to hit the Silurian Hypothesis head-on and ask whether an earlier industrial civilization could have risen, burned hard, collapsed, and been almost completely erased by erosion, plate tectonics, and deep time, leaving behind only carbon spikes, strange metals, plastic-like residues, and nuclear ghosts for us to find. The question behind the Silurian Hypothesis is direct. Was there ever an industrial civilization on Earth long before humans, one that used large amounts of energy, built large-scale infrastructure, changed the climate, and then disappeared so completely that almost all of its traces were wiped out? This idea was laid out by two scientists, astrophysicist Adam Frank and climatologist Gavin Schmidt, and their goal was not to sell a conspiracy. Their goal was to test something uncomfortable. How visible is a civilization like ours in the geological record after tens of millions of years? You're not asking, are there aliens out there right now? You're asking a more focused question. Are we the first industrial civilization on Earth, or just the latest one in a sequence you have never noticed? The Silurian Hypothesis does not assume ancient reptile engineers or lost human empires. It starts from a simple point. Assume, as a thought experiment, that some species reached an industrial phase 100 million years ago. What evidence would survive today? And would you even recognize it as technological, or would it look like just another natural climate event? Before you answer, you need to see how small your own timescale is. Modern humans have existed for roughly 300,000 years. For most of that time, you had stone tools, small groups, and no large cities. Agriculture, the thing that lets you settle down and build permanent settlements, is only about 10,000 years old. The industrial era, where you burn fossil fuels at scale and run factories and power grids, is around 200 years old. Now line that up against the age of the Earth. The planet is about 4.54 billion years old. Complex multicellular life has been around for more than 500 million years. Dinosaurs ruled for around 165 million years. Your entire industrial phase so far is a 200-year slice inside hundreds of millions of years where other intelligent, tool-using, energy-hungry species could have developed and vanished. If you compress Earth's history into a single year, your industrial age is less than the last second before midnight. Here is the key problem. If another civilization had its own 10,000-year industrial burst 100 million years ago that still fits easily inside those huge stretches of time, there are many windows, tens of millions of years long, where something could have risen to global power and then disappeared, long before the first humans walked upright. So instead of asking, is that likely, the Silurian Hypothesis asks first, would we even be able to see it if it happened? That leads to the core question, detectability. The hypothesis is not trying to claim that earlier civilizations did exist. It is trying to measure how strong the footprint of industry really is. Take your civilization as the test. Right now, you are burning fossil fuels, changing the atmosphere, mining metals, making plastics, and spreading synthetic chemicals across land and sea. If geologists in a far future, maybe 100 million years from now, drilled through the rocks from this time, what exactly would they see? How many clear signals would still be there? And how many would have been erased by erosion and plate tectonics? Think about what you're already leaving behind. Since the 18th century, humans have put more than 2,400 gigatons of carbon dioxide into the atmosphere. Global average temperatures have already gone up by about 1.2 degrees Celsius, around 2.2 degrees Fahrenheit. You produce over 400 million tons of plastic every year. Synthetic chemicals, including long-lasting forever chemicals, are now found in soils, rivers, oceans, even in remote Arctic ice. All of this is measurable right now as a distinct signal. In geological terms, that signal turns into a layer. Future scientists would see a jump in carbon in sediments, a shift in the ratio between different types of carbon atoms, a rapid warming trend preserved in oxygen isotopes and fossils, a spike in unusual metals from mining and industry, traces of synthetic molecules, and a change in the kinds of fossils above and below that layer. The important point is this: you already know that a technological civilization can leave a global mark in just a couple of centuries. The Silurian Hypothesis pushes that forward in time and then runs it backward. If our mark is this strong after 200 years, what would it look like after 100 million years of burial and partial destruction? How much of the plastic survives? How much of the carbon spike is still clear? How obvious are the metal anomalies? Do the synthetic chemicals fully break down, or do they leave subtle but detectable patterns? This is where it stops feeling like science fiction and turns into a research question. To know whether someone could have come before us, you have to first know what parts of our own civilization are robust enough to survive deep time. That forces you to turn climate records and sediment cores from seafloor and land into a forensic toolkit. You're learning how to read Earth as a crime scene, except the suspect is not a person. It is an industrial phase in the planet's history. Here is the twist. Every action you take today, every kilometre you drive, every kilowatt hour you use, every bit of plastic you throw away is part of that experiment. Whether you like it or not, your civilization is writing a data point into the rocks, a reference signal for what an industrial species looks like in geology. If no one came before you, future scientists can still use your layer to search other planets and to set limits on what might have happened on Earth before humans. If someone did come before you, and you eventually learn to see their trace, then the story gets even more serious. So the real tension is this: deep time is huge, your history is tiny, and the planet is not good at keeping records. That means you cannot simply point at the ground and say, "We see nothing, therefore nothing was ever here." You need to do the harder work. You need to understand how many civilizations could fit into Earth's past, and how easy it would be for most of their traces to be lost. That is where we go next, into the scale of deep time, and how many chances this world has had to run the experiment of civilization. How many times has this planet had all the right conditions for a civilization like yours to rise up, burn hard, crash, and disappear long before you showed up? To answer that, you have to zoom out to deep time. For roughly the last 540 million years, Earth has been in a phase geologists call the Phanerozoic. That's the era with complex multicellular life that you'd recognize in a picture. Trilobites early on, then huge forests, dinosaurs, birds, mammals, flowering plants. This is the part of Earth's history where you get big animals walking on land, complex food webs, and enough biological complexity that something smart and tool-using could, in principle, evolve. Now, an industrial civilization isn't just any life, it needs specific conditions. It needs a lot of oxygen in the atmosphere, because oxygen's what lets you burn fuel efficiently and run high-energy metabolisms. It needs stable continents, big blocks of land that stay above water for long periods, so large brains and hands and technology can develop on solid ground, not just in the ocean. For at least the last 200 to 300 million years, oxygen levels in Earth's atmosphere have been roughly similar to today, around 21%. That's enough for big animals with high energy needs, enough for fire, enough for metalworking and industry. In other words, for the last couple of 100 million years, the planet has not just been alive, it has been in a mode that can support something like us. So you already have multiple long windows where energy-hungry land-dwelling intelligences could appear. These windows are not short, they are tens of millions of years long. Inside each window, evolution can run many experiments. Species appear, spread, and die out. Entire ecosystems rise and fall. There is no rule that says humans were the only possible outcome, or that intelligence had to happen only once, right now. So where do you sit on that timeline, really? Your industrial era is around 200 years old. That is the entire span of large-scale fossil fuel burning, railroads, power grids, electronics, rockets. Dinosaurs, just as one comparison, dominated Earth for about 165 million years. Not 165 years, 165 million. They had orders of magnitude more time than you've had so far. From the start of the Triassic period, when the first dinosaurs began to show up, to today, you're talking about roughly 250 million years of history. Now do a simple thought experiment. Say every 50 million years or so, conditions are good enough that there's a real chance an industrial civilization could appear somewhere on Earth. You don't even need that to be likely, you just treat it like rolling a set of dice. Over 250 million years, you'd roll that set several times before humans ever emerged. That doesn't prove anyone else actually made it to industry, but it shows you something important. There was not just one opportunity, the human opportunity, there were many. Even if evolution only rarely stumbles into smart plus tool use plus fire plus social cooperation, the planet has had a lot of time to try. You live on the latest layer of a very long stack of experiments. The real question is not, could it ever happen? Because you are proof it can. The question is, did it happen before, and if it did, would anything survive for us to see? Now you run into the next problem. Earth is terrible at long-term memory. The crust you stand on is not fixed, it is moving. The planet's outer shell is broken into tectonic plates that drift at centimeters per year, similar to how fast your fingernails grow. Where plates collide, one plate often dives under another, in a process called subduction, carrying seafloor down into the mantle, where it heats up, deforms, and gets recycled. Most of the oceanic crust on Earth today is younger than about 200 million years. The seafloor that existed when the early dinosaurs were walking around, that entire landscape has mostly been dragged down and destroyed. Only fragments are left in a few special places. That means any ports, underwater cables, offshore farms, or coastal cities built on that ancient seafloor would not just be buried. They'd be gone, melted, and mixed into new rock. Continental crust is older and more stable, but even there, erosion and mountain building constantly reshape the surface. Only a small fraction of Earth's surface, less than about 10%, preserves rocks older than 1 billion years. That's out of 4.54 billion years total. The rest has been reworked, warped, or erased. So if someone built a city on a coastal plain 150 million years ago, in many cases that plain is now an eroded plateau, a mountain range, or a subducted margin. The foundations of that city are either deep underground, smashed into rubble, or turned into magma. Now take our own structures and drop them into that moving, grinding environment. How long do they really last? Concrete, steel, glass, asphalt, all of it is strong on human timescales but weak on geological ones. Concrete starts cracking and weathering in thousands to tens of thousands of years, long before you hit 1 million. Steel rusts away faster, especially in wet or salty environments. Even the pyramids in Egypt, which feel incredibly old to you at about 4,500 years, are already visibly worn down by wind and sand. Stretch that to 10 million years, 100 million years, with freeze-thaw cycles, rain, chemical weathering, earthquakes, and slow uplift or subsidence. Recognizable skyscrapers, bridges, and roads do not survive that kind of punishment. They break down, collapse, get buried, and their materials disperse. After enough time, you're not going to walk into a valley and see a fossilized city skyline. The survival probability for intact, recognizable structures over tens of millions of years is effectively zero. So if you want to look for another civilization in deep time, you should not be expecting walls and streets. You should be expecting much more subtle traces, changes in the chemistry of rocks and sediments, unusual patterns of metals, odd isotopes, strange molecules that don't match normal biological processes. The real fossils of industry are chemical, not architectural. This leads to a kind of deep time humility. When you spread your 200-year burst of industry across hundreds of millions of years of geological history, you don't get a big chapter, you get a thin line. In a sediment core drilled from the seafloor in the future, your entire industrial layer might be just a few centimeters thick, say around 10 centimeters, roughly 4 inches. Inside that slice, future scientists would see a sudden jump in carbon, a sharp warming signal, plastic fragments turned into tiny grains, metal anomalies, and a shift in fossils. Outside that slice, above and below, the planet looks more normal again. If some other civilization came before you and had its own short industrial phase, its entire story would also be compressed into one of these thin slices. A few centimeters of odd chemistry in a column of rock that is hundreds or thousands of meters tall. That is the scale you're dealing with. That's how easy it is for whole cycles of rise and collapse to be reduced to a narrow, easily missed layer. So the next question is obvious. If whole civilizations can be squeezed into a few centimeters of rock, and most of the planet's surface is constantly being recycled, how much of Earth's real history are you actually seeing, and how much has already been shredded? You live on a planet that is constantly trying to erase you, not out of malice, just because that's how the physics and chemistry of a rocky world work over long time scales. Start with the ground under your feet. On continents, typical erosion rates are around 0.01 to 0.1 millimeters per year. That sounds tiny, about the thickness of a human hair, shaved off the surface every year. But stretch that out. Over 1 million years, that's 10 to 100 meters of rock removed, 33 to 330 feet. Over 10 million years, it adds up to 100 to 1,000 meters, roughly 330 to 3,300 feet stripped away, moved downhill, and dumped into rivers, deltas, and oceans. So take any modern city, pick New York, Tokyo, it doesn't matter. Now place that city with its skyscrapers and highways and subways and a landscape that is going to sit there for 10 million years. With erosion at those rates, that original surface is either gone or deeply buried. The tallest towers are ground down, the streets collapse, the foundations crack and sink. Even if some concrete slabs or steel chunks survive as physical pieces, they get broken apart, mixed with sand, mud, and gravel, and carried away. After enough time, what's left are scattered fragments inside natural-looking sediments. Without context, they look a lot like weird rocks. Now scale up from erosion to the full rock cycle. The outer shell of Earth is made of plates, and those plates move a few centimeters per year, similar to how fast your fingernails grow. Where plates meet and one dives under the other, at subduction zones, oceanic crust is dragged down into the mantle. Over about 200 million years, that conveyor belt has recycled almost all of the seafloor. The actual ocean bottom that existed when early dinosaurs walked on land is mostly gone, turned into new rock at depth and later pushed up elsewhere. Think about what that means for anything built on the oceans. Ports, offshore platforms, huge undersea cables, seafloor mining operations, all the big infrastructure you associate with a mature industrial civilization. It sits on crust that is geologically temporary. Give it a couple of 100 million years, and that whole surface with all its structures is dragged down, heated, crushed, and chemically altered. The rock cycle does not work like a library. It does not store clean labelled layers for you. It works more like a recycling system, constantly breaking down old material and making new crust out of the pieces. You might think, okay, but fossils survive, so why not our stuff? The catch is, fossils are rare too. Only a tiny fraction of all the organisms that ever lived end up fossilized. To make a fossil, you usually need rapid burial, in mud, sand, or volcanic ash. You need low oxygen so the body doesn't rot completely, and you need the right minerals to seep in and solidify the remains. Most animals die and disappear, eaten, decomposed, or scattered. For artifacts, the requirements are similar. A metal tool, a circuit board, a building has to get buried quickly, in the right environment, and then sit undisturbed for long periods if you want it preserved. Now think about how many fossils we have from entire ancient ecosystems. Sometimes a whole species is known from a single jawbone or one tooth. That's from millions of years of animal life. If you now take a short industrial civilization, maybe 10,000 years from first steam engines to collapse, the odds that any of its advanced devices make it into the fossil record in a recognizable way are very low. look at what we can see from our own past. Some of the oldest large human structures, like Göbekli Tepe in modern Turkey, are about 11,000 years old. They are already heavily weathered and partially buried. Most ancient city sites, even in dry regions, have only around 10 to 12 meters of layered ruins, about 30 to 40 feet, before you hit older ground. That's after a few thousand years of building, rebuilding, and stacking new structures on top of old ones. Now run this forward. Go another 100,000 years. Surface structures crumble, roofs cave in, walls collapse, everything fills with soil and sediment. Rivers shift, new layers build up on top. To a future observer, the city is just a slightly unusual patch of rock and soil, unless they dig in exactly the right place, and even then, details are blurred. Push to 1,000,000 years, and any remaining shapes are basically gone. At that point, you are no longer doing archaeology, you're doing geochemistry. You aren't looking at streets and foundations, you're looking at tiny changes in what the rocks are made of. So what actually stands a chance of surviving deep time? Not the buildings themselves, but the signals they leave behind. Industrial civilization changes what gets deposited in sediments. It changes which metals are mobilized and where they end up. It alters the ratios between different isotopes, different versions of the same element, like carbon or oxygen. It creates complex synthetic molecules that never existed before, and then spreads them through water, air and soil. In a sediment core, drilled from the seafloor or a lake bed, those changes show up as layers with unusual composition. Maybe there's a spike in certain metals like copper, lead or rare earth elements that doesn't match normal volcanic or mineral processes. Maybe the ratio of carbon isotopes suddenly shifts in a way that lines up with large-scale burning of fossil fuels. Maybe strange organic molecules appear that do not look like anything biology usually makes. If you want to search for an ancient civilization, this is the kind of thing you have to hunt for. You are not Indiana Jones walking into a buried temple. You're more like a chemist in a lab, measuring tiny differences in mud and asking whether those differences could only come from nature, or whether they point to an industrial event. The planet is erasing the big, obvious stuff, the skyscrapers and highways, but it cannot completely erase the chemical footprints of massive energy use and large-scale industry, not without leaving at least some distortions behind. This is where the tension ramps up, because one of the strongest and clearest signals our civilization is putting into the rocks is tied to carbon and climate. You're already pushing the atmosphere and oceans into a new state, and that shift will be written into future rock. The question is, are there older, similar climate shocks in the record that might not be purely natural? How do you tell the difference between a planet having a volcanic outburst and a planet having an industrial phase? That's what we need to unpack next when we look at carbon ghosts and the climate signatures of industry. Right now, the air around you is carrying a clear, measurable signal that this planet is in an industrial phase, and that signal is made of carbon. Before factories and engines took over, atmospheric carbon dioxide sat at about 280 parts per million, 280 CO2 molecules for every million molecules of air. Today it's over 420 parts per million. That jump of about 140 parts per million in roughly 200 years is brutally fast on geological timescales. When scientists drill ice cores from places like Antarctica and Greenland and measure old bubbles of air trapped inside, the change looks almost like a vertical line, a sudden wall, not a gentle slope. Now move that picture into rock. The ice eventually melts, the air mixes away, but the effect of that CO2 stays in the climate system. Higher CO2 means higher temperatures, and that shows up in tiny chemical shifts in things that form in that era, like shells of microscopic organisms and minerals in sediments. One key proxy is the ratio of different forms of oxygen inside those shells, which tracks temperature. So in a future rock column, your industrial moment becomes a thin band, maybe just a few centimeters thick, where the carbon content jumps, the oxygen-based temperature signal jumps, and everything above and below looks calmer. That band is what people mean when they talk about the Anthropocene signature, the human-made layer. It's not a big, obvious stripe of concrete, it's a subtle chemical fingerprint, To a far future geologist, that layer will basically shout, "Something suddenly dumped a lot of CO2 into the air and oceans, and the planet heated up quickly." The key point is, you've already proven that an industrial civilization can leave a detectable climate mark in a relatively tiny amount of time. To sharpen that fingerprint, you have to look not just at how much carbon is in the system, but what kind of carbon it is. Carbon atoms come in slightly different versions, called isotopes. The two important ones here are carbon-12 and carbon-13. Both are stable, but carbon-12 is lighter. Plants prefer to use the lighter version when they build themselves, and over millions of years, that plant material becomes coal, oil, and natural gas. So fossil fuels are rich in carbon-12 and relatively poor in carbon-13. When you burn those fuels, you take that light carbon and dump it into the atmosphere and oceans. That lowers the ratio of carbon-13 to carbon-12 in the global carbon cycle. Scientists measure this as a value called δ11⁻C, basically how much the ratio deviates from a standard. Since the Industrial Revolution, that value has been drifting downward, a clear sign that fossil fuel carbon is taking over. This effect is already so clear it has a name, the Swiss effect. It's one of the most solid pieces of evidence that the CO2 increases from fossil fuels, not volcanoes or some other source. Now connect that to the Silurian Hypothesis. If a past civilization burned large amounts of fossil carbon, it would leave the same style of mark. You'd expect to see a sharp negative shift in that carbon-13 to carbon-12 ratio in sediments and organic material laid down at that time, globally, not just in one local basin. That's a carbon ghost of industry. You don't see the factories, you see the isotopic trail they left behind. Then you ask, has the planet done anything like this before? About 56 million years ago, Earth went through an event called the Paleocene-Eocene Thermal Maximum, or PETM. During the PETM, global average temperatures rose by roughly 5 to 8 degrees Celsius, about 9 to 14 degrees Fahrenheit, over less than 20,000 years. In climate terms, that is very fast. In the sediments from that time, you see a big negative δ11⁻C shift, meaning a lot of light carbon suddenly entered the system. You also see major changes in tiny marine fossils, showing oceans got warmer and more acidic. Estimates for how much carbon was released during the PETM run into the thousands of gigatons, in the same ballpark as what humans could emit by the year 2300 if we burned most of our fossil fuel reserves. In other words, PETM looks, at first glance, like a natural analogue of our current trajectory. Big carbon dump, fast warming ecosystem stress. The standard explanations involve massive volcanic activity, destabilization of methane locked in seafloor ices, or other natural feedbacks. The Silurian-style question lurking behind that is simple. Could an event that looks roughly like us, in terms of carbon and temperature, ever be artificial instead of natural? To push on that, you need to think about rate versus magnitude. Magnitude is how much warming, how much carbon. Rate is how fast did it happen. Human-driven climate change is extreme on the rate axis. We're changing CO2 and temperature over decades to centuries. Natural carbon cycle disruptions in the deep past typically play out over thousands to hundreds of thousands of years. So if you want a smoking gun for industry, you look for δ11⁻C changes that are not just large but extremely abrupt. You want a cliff, not a gentle hill. But there's a big problem. Sediments don't record time at high resolution forever. On the seafloor, you might get a few millimeters of new mud every 1,000 years. Over millions of years, compaction and chemical changes squeeze and smear those layers. A 10,000-year spike could end up recorded in just a few millimeters or a centimeter or two in a core. That blurs the timing. In the rock record, a sharp human speed event and a much slower, purely natural event can both look like a single thin band with a carbon anomaly. That makes it hard to say, just from one core, whether something was industrial or volcanic. There's another angle, though, that doesn't rely only on greenhouse gases. Every time you use energy, whether it's coal, gas, nuclear, or solar, that energy eventually turns into heat. Right now, global primary energy use is on the order of 600 exajoules per year, That averages out to about 19 terawatts of continuous power output. For comparison, the Sun delivers around 170,000 terawatts to Earth. So human waste heat today is tiny compared to sunlight, about 1/10,000th of the solar input. It doesn't drive climate by itself, the greenhouse effect does most of the work. But scale civilization up in your mind. If a planet-wide society tapped a huge fraction of its star's energy through orbiting collectors, fusion, or something more exotic, its waste heat could become comparable to natural energy flows. At that point, even if they used very clean energy sources, with no CO2 emissions, their mere existence would warm the planet. You'd get a baseline temperature bump that doesn't match the levels of greenhouse gases in the air. In the rock record, that might show up as an interval where temperature proxies, like those oxygen isotope ratios, show persistent warmth that can't be fully explained by CO2, methane, or changes in the planet's orbit and tilt. It would be subtle, because nature can also do strange things, but combined with carbon anomalies and other technosignatures, it would strengthen the case for an industrial cause. So at this point you have a picture where carbon, isotopes and heat form one class of clues. They tell you that something dumped energy into the system very fast over a short time. But carbon and heat alone are not enough to be sure. Volcanoes, methane release and natural feedbacks can mimic parts of that footprint. To push further, you have to look for things that nature doesn't make on its own at all, like synthetic materials and engineered combinations of elements. That's where your plastic, metal and concrete layer comes in, the part of the story where trash itself becomes a fossil. How do you know you're in an industrial age, even if every building vanished, every power plant shut down and every server went dark? The answer is simple. The planet is filling up with your trash. You live in what a lot of scientists now casually call the Plasticine. Every year, humans produce hundreds of millions of tons of plastic. These are long-chain polymers, things like polyethylene, polypropylene, PVC, PET. They are built to be tough, light and cheap, not to break down quickly. You have pushed them into every environment you can name. They're in soils, on beaches, in riverbeds, floating in surface waters, and raining down into the deep ocean. Microplastics have already been found at the top of Mount Everest, around 8,848 meters, about 29,029 feet above sea level, and in deep ocean trenches more than 10 kilometers down, around 6 miles below the surface. That tells you something important. This material is not local, it is global. As sediments pile up, the plastic mixed into sand, mud, and biological debris will be buried. In future rock, this turns into a layer with synthetic carbon-rich flecks and fibers embedded in it, a kind of artificial sediment made out of your waste. Here's the next step. Plastic doesn't just sit there unchanged on the surface. Sunlight, especially ultraviolet light, breaks chemical bonds. Waves, wind, and abrasion grind large pieces into smaller ones. So big bags, bottles, and fishing nets crack, fragment, and turn into microplastics and nanoplastics. That doesn't mean they disappear. It means they become harder to see with your eyes, but easier to mix into everything else. In low oxygen environments, like some seafloor sediments, these tiny plastic pieces can be quite stable. Some studies suggest they could persist for hundreds of thousands to millions of years if they are buried and cut off from strong oxidation. Over even longer times, they may slowly break down into simpler hydrocarbons or amorphous carbon-rich residues. But the key point is this. You still get a distinct layer where the organic material looks different from normal. It is enriched in weird, polymer-derived compounds. That layer is like a plastic horizon in the rock record, a time slice that says, this is when a species started turning old fossil carbon into new synthetic solids and dumping them everywhere. Plastics are only one part of the technological fossil story. Think about metals and construction materials. Humanity produces over 60 million tons of aluminum every year. In nature, aluminum is almost never found as pure shiny metal. It oxidizes fast and is usually locked in minerals like bauxite or feldspar. To get pure aluminum, you need high temperatures and industrial chemistry. So if you drill into rocks that are 100 million years old and find chunks or grains of relatively pure aluminum or odd aluminum alloys, that is not something you shrug off. That is a technofossil, a trace that strongly hints at technology. The same goes for carefully tuned alloys. Stainless steel has specific mixes of iron, chromium, nickel and other elements in ratios that don't happen by accident. High-temperature superalloys have exotic combinations of metals designed to survive in jet engines. If those corrode and get buried, they might turn into minerals with very unusual elemental patterns. Add to that artificial concrete, which is basically human-made rock. It's a mix of cement, sand, gravel and water that hardens into a material with a distinctive texture and chemistry. If, far in the future, you see thick layers of this weird uniform rock spread around former coastlines and the river valleys, you are not going to call it natural. Then there are the molecules you can't see but that still mark your era. Industrial society has invented thousands of synthetic organic compounds, complex carbon-based molecules that no organism ever needed before. Some of them, like PCBs and PFAS, are extremely stable and spread around the globe. They are detectable in water and in animal tissues at levels of parts per trillion. That's like a few drops in an Olympic swimming pool. In sediments, especially fine-grained muds, they can get trapped and preserved. To a future geochemist, these would show up as a suite of unusual molecules clustered in a narrow time slice. They would not match any known natural biosynthetic pathway. No plant, microbe or animal makes that exact pattern of chlorine-laden, fluorine-laden or fluorocarbon structures. For a hypothetical ancient civilization, you would expect the same type of thing, their own custom chemical toolkit, leaving behind a fingerprint of strange compounds in a thin layer of mud. Now here's a subtle problem that raises the tension. At very long timescales, the exact polymer structures in plastics may not survive. Heat, pressure and chemistry in the subsurface can break long chains into short ones, or turn them into more generic carbonaceous material. After tens of millions of years, the clear "this is polyethylene" signal could be gone. What might remain is just an organic rich layer with odd properties, a bit like some natural oil shales or coal seams. Without context, that could be misread as purely natural. So when you look at Jurassic or Cretaceous rocks and say, "We don't see any obvious plastic, so there was no ancient tech," that conclusion is not solid. All you can safely say is, with the current resolution of our chemical scanning, we haven't seen anything that obviously screams machine-made. That is not the same as saying it is impossible. It might mean you haven't looked at enough samples, or with the right instruments, or at the right scales. Put all this together and you get a clear message. If an industrial civilization develops, it turns whole parts of the planet into a composite material, a mix of natural sediment and synthetic stuff. Plastics, metals, cements, and designed molecules. That composite becomes a fossil of technology. The question now is, where does that fossil get stored best? And how fine is your time resolution when you go looking? To answer that, you have to go to the oceans and treat the seafloor like a slow, blind recorder of everything that happens on the surface. The most accurate long-term record of what Earth has been doing is not on land. It's in the mud at the bottom of the oceans, and that's where you'd have to go if you seriously want to test whether anyone was here before you. Most of the sediment that Earth produces ends up in the sea. Tiny particles are constantly falling through the water column, dust blown off continents, shells of dead plankton, bits of clay, volcanic ash, chemical precipitates. The rates are slow, often millimeters per 1,000 years, but they never really stop. Layer after layer builds up. If you drill a few hundred meters down into that seafloor, you are literally moving through tens of millions of years of history. Programs like the Integrated Ocean Drilling Program have pulled cores over 2 kilometers long, around 1.2 miles, and each section of that core is a slice of time stacked one on another. This is why the oceans hold the best memory. Continental surfaces get eroded, uplifted, and destroyed in a messy way. The deep sea floor, especially in the big ocean basins far from plate boundaries, is quieter. Sediment just keeps accumulating. It's not perfect, There are gaps, but compared to almost anywhere on land, it's about as close to a continuous tape as you're going to get. If a civilization changed the global environment, this is where the bulk of the signal would eventually end up. Now comes the catch: resolution. Even in high-quality sediment cores, time is compressed. A single centimetre of mud, 0.4 inches, can represent hundreds to thousands of years. A short violent event that lasts 10,000 years can get squashed into a layer a few millimetres thick. That's thinner than your fingernail. Our entire industrial civilization so far is only about 200 years long. In many cores, that would be less than a single sampling interval, basically one analytical data point. To actually detect a civilization as brief as ours, you need extremely dense sampling. You can't just take one sample every 10 centimetres and call it a day. You'd need to slice through that core at sub-millimetre spacing, then run very sensitive instruments on each slice looking for tiny shifts in chemistry, fossils, and physical properties. Right now, we don't do that systematically across the whole seafloor. We have drilled only a small fraction of the oceans, and mostly in areas that are interesting for standard geology and climate question, not for the technosignature hunting. It's like trying to understand an entire library by pulling one page out of every 100th book and reading that page once. So what do we actually measure in these cores? Scientists look at microfossils, tiny shells from organisms like foraminifera and diatoms. Changes in which species are present can tell you about water temperature, acidity and nutrient levels. They measure grain sizes to see whether currents were stronger or weaker. They check magnetic properties, which record changes in Earth's magnetic field and help with dating. They analyse isotopes like carbon-13 and oxygen-18, which track the carbon cycle and global temperatures. They also measure trace metals like iridium for meteor impacts, or various metals linked to volcanic activity and erosion on land. From that toolkit, you can already see big events. The layer marking the asteroid that killed the non-avian dinosaurs has an iridium spike, spherules from melted rock, and a shift in fossils. Hyperthermal events like the PETM show up as big negative shifts in carbon isotopes and changes in microfossil communities. Volcanic eruptions leave ash layers and metal fingerprints. If an industrial civilization dumped large amounts of pollutants into the oceans, changed erosion patterns, or altered nutrient flows at a global scale, you'd expect some of those proxies to react. You might see sudden jumps in certain metals, unusual organic molecules, or a rapid shift in what kinds of microfossils are thriving or dying off. The problem is, not every anomaly is well explained, and not every anomaly is obviously technological. There are still parts of the stratigraphic record where you see sudden warming, local metal enrichments, or odd extinction patterns, and scientists argue about the exact cause. Usually, the leading explanations involve natural mechanisms, volcanic outgassing, changes in Earth's orbit and tilt that alter sunlight patterns, release of methane from seafloor ices, shifting ocean currents. The Silurian Hypothesis doesn't throw those explanations away. It adds a mental note in a small number of cases where several independent signals line up. You should at least check whether an industrial cause could fit the data. So what does line up mean here? You'd be especially interested in layers where you see at the same time a big carbon isotope excursion, a rapid warming signal in oxygen isotopes, unusual patterns of metals that don't match normal volcanic fingerprints, and traces of molecules that are complex and hard to make by simple geologic processes. All of that compressed into a very thin time slice. If you see just one of those things, it's probably natural. If you see 3 or 4 together, tightly clustered, it becomes more reasonable to ask whether you might be seeing a technological event. At the moment, with the cores and analyses we have, there is no widely accepted layer that screams ancient industry. That is important. It means there is no obvious planet-wide technosignature that looks just like what we're doing now, but you have to be precise about what that absence really tells you. We have only sampled a small part of the seafloor. Most cores are not scanned at the ultrafine resolution you'd want for this search, and even when you see something odd, natural explanations can be hard to rule out completely. So the honest conclusion is narrow. If there was a prior civilization, it did not leave a simple global scale, in-your-face signal identical to the one we are currently creating. It probably didn't burn fossil carbon at the same intensity, for the same duration, across the whole planet, or if it did, that signal has been smeared, buried, or destroyed beyond the resolution of our current tools. It might have been smaller, shorter-lived, regionally constrained, or more careful with its waste. And that opens up a sharper question: if the seafloor mud is this hard to interpret, even for our own civilization, which we directly understand, how well can you really trust the fossil record to rule out past industry, especially during periods of major disruption? The biggest disruptions you know about are the mass extinctions, times when most life on Earth took a hit. Are those always natural resets? Or could a few of them hide something else behind the chaos? That's where the tension goes next. When your planet wipes out most of its own life, are you always looking at blind geology? Or could you sometimes be seeing the side effects of something intelligent that pushed too far? Earth has had at least 5 moments where things went really bad: end-Ordovician, late Devonian, end-Permian, end-Triassic, end-Cretaceous. Each of these mass extinctions killed roughly 70 to 90% of species. Some played out over a few million years, others much faster. Whole ecosystems collapsed, food webs broke, dominant groups vanished. After each one, evolution rebuilt the system with whatever was left. Right now, you are driving a new crisis. Species are disappearing tens to hundreds of times faster than the natural background rate. Large animals are shrinking in range, coral reefs are bleaching, forests are being cut, oceans are acidifying. Many scientists call this the 6th mass extinction, and unlike the first 5, this one clearly has a technological species at the center of it. You are the test case that proves an industrial civilization can behave like a geologic catastrophe. So ask the next question directly. If a technological civilization existed long before humans and reached global scale, what would it do to biodiversity? You already know the mechanisms: habitat destruction, overfishing, invasive species moved around the globe, rapid climate change from greenhouse gases, widespread pollution. All of that pushes species toward extinction. In the fossil record, that doesn't look like we see factories. It looks like this: many species disappearing from the layers over a relatively short interval, followed by a spike in simpler, opportunistic species that can handle disturbed environments. You'd see forests replaced by scrub and weeds in pollen records, large animals replaced by smaller, generalist species in bones and teeth. It's the same kind of pattern you're driving now, just smeared out in rock instead of headlines. One extinction in particular looks disturbingly close to what a runaway civilization could cause, even though the standard explanation is natural. Around 252 million years ago, at the end of the Permian period, Earth went through the biggest known mass extinction. About 90% of marine species died out, and around 70% of land vertebrates disappeared. That's almost a total reset for complex life. The leading explanation is massive volcanic activity in what is now Siberia, called the Siberian Traps. For a long time, huge volumes of lava erupted, releasing enormous amounts of carbon dioxide and other gases. CO2 went up. Global temperatures climbed by roughly 5 to 10 degrees Celsius, about 9 to 18 degrees Fahrenheit. Oceans lost oxygen and turned hostile to many forms of life. Toxic metals and other pollutants increased. From a distance, that sequence looks eerily like a planet-scale industrial accident. Huge carbon release, poisoning, overheating, and collapse. The key point is, natural processes can already create signals that look similar to what an industrial civilization could do. This is exactly why the Silurian hypothesis has to be careful. When you see a huge carbon spike and warming, you cannot just jump to someone did this with technology, because geology alone is powerful enough to break the system. The end-Permian event is a reminder. Even the worst thing you could do with industry has a natural twin somewhere in the record. Then there are events that clearly come from outside, like the one that ended the age of non-avian dinosaurs. About 66 million years ago, an asteroid slammed into what is now the Yucatan Peninsula in Mexico. It released energy equivalent to billions of Hiroshima bombs, carved out a crater about 150 kilometers wide, around 93 miles, and blasted dust and sulfur high into the atmosphere. Sunlight dropped, temperatures crashed, photosynthesis stalled, food chains collapsed. Most dinosaurs died out, along with many marine species. To you, that impact is a clean story, big rock from space, bad day for dinosaurs. But shift your perspective. If a new civilization arises 100 million years from now and looks back, they see an impact layer, a sudden extinction, then a long gap before humans appear. They might reasonably ask, did anything technological emerge in the tens of millions of years before that asteroid? Something that never made it to full global dominance. The rock record around that time would not easily answer that, because the impact itself and the chaos it caused would overprint many subtler signals. That leads to a harder idea. Could a civilization generate its own mass extinction, then collapse so fast that its signature is mostly local, not global? You're already seeing how a tech species can damage specific regions far more than others. Some coastal zones are overloaded with nutrients and go hypoxic. Some rivers carry heavy metal loads from mining. Some areas have extreme pollution from industry, while other regions stay relatively clean. If a past industrial species rose on one continent, pushed its environment too far and crashed before it spread everywhere, its main signatures might be confined to that region. Maybe you'd see heavy metal enrichment, synthetic-looking mineral assemblages, and sharp ecosystem changes in one basin, while other continents look normal. Over hundreds of millions of years, erosion could strip away much of that surface, and plate tectonics could drag parts of it down at subduction zones. What's left might be scattered patches of strange rock in a few places you simply haven't drilled yet. There's a paradox here. The larger and more global a civilization becomes, the easier it is to detect in the rock record, because it changes the entire planet, not just one area. But the larger and more global it becomes, the more unstable it might be, because it pushes closer to planetary limits. It burns more energy, moves more material, and amplifies feedbacks. That can shorten its lifetime. A small local industrial phase might last longer, but be harder to see. A huge global one leaves a stronger trace but may burn out quickly. You are now living inside a test of that idea. You are large enough and active enough that you are clearly driving extinctions and climate shifts. If you scale up further, you make your geologic signature louder, but you also put more pressure on your own survival. From a far future point of view, that outcome is binary. Either you become a thick, obvious disaster layer that future scientists can't miss, or you manage to control your impact and your changes blur into the natural noise of the planet. If mass extinctions can be triggered by both blind geology and intelligent activity, then every big crash in the past is not just a story about volcanoes and asteroids. It is also, at least in principle, a place to quietly ask, did anyone push this system, or was this all nature? To get beyond that question, you need to look past extinctions and into more specific technological fingerprints: metals, isotopes, nuclear traces, and engineered materials baked into the rock. That's where the search turns from life did something to something that understood atoms and energy was here. Right now you are doing something to Earth that normal geology does not do. You are rearranging the periodic table on a massive scale. Modern mining moves billions of tons of rock every year. You dig up copper, iron, gold, uranium, rare earth elements, and you pull them out of their natural mixtures. You concentrate them into ores, refine them, turn them into products, and dump the leftovers into waste piles and tailings. In geological terms, that means you are taking elements that were once spread out through huge volumes of rock and focusing them into narrow layers and patches with very specific compositions. In the rock record, that looks like sudden spikes in certain metals, and those spikes have patterns that do not match normal processes like volcanoes or sediment sorting. Rare earth elements are a good example. Nature produces specific patterns of these elements in igneous rocks and sediments, ratios that geochemists know well. Electronics, magnets, and batteries, on the other hand, use unusual combinations. If you drilled into a layer 100 million years from now and found that neodymium, dysprosium and terbium were all enriched together in proportions that match modern high-performance magnets, you would not call that a normal rock. You would have to ask, who or what moved those elements into that pattern? Then there is the nuclear layer you're creating. Nuclear reactors and nuclear weapons tests generate isotopes that do not appear in significant amounts in nature. Plutonium-239, cesium-137, strontium-90 and many others. Each of these has a characteristic half-life. Some decay on the scale of decades, others stick around for thousands or millions of years. Over millions of years, most of the original radioactive atoms decay away, but they leave behind daughter products and altered isotope ratios in whatever material they touched. Think about what an above-ground nuclear test does to the ground under it. You can melt sand and soil into glass-like material. The classic example is trinitite, the greenish glass formed at the Trinity test site. It is basically fused sand loaded with weird isotopes and trace metals from the device. You can also get vitrified layers from reactor accidents or from deliberate underground tests. Over deep time, the radioactivity drops, but the glassy textures, the unusual chemistry and the shifted isotopic ratios can stay locked in the rock. There is even a natural example that shows you what to look for. Around 1.7 billion years ago, in what is now Oklo in Gabon, uranium deposits happened to have just the right concentration and water flow to go critical. They ran as natural nuclear reactors for hundreds of thousands of years. Those reactors left clear signatures, uranium with an unusually low amount of uranium-235, specific patterns of fission products, and altered isotopic ratios in surrounding minerals. Oklo is important for two reasons. First, it proves that nuclear-style anomalies can be natural, so you can't automatically blame every strange isotope pattern on technology. Second, it gives you a template. If you find something that looks like a reactor signature into rocks that should not host natural reactors, or combined with other technosignatures like plastics or strange metals, then you have to seriously consider a technological origin. You would be looking at a nuclear footprint without a modern human cause. On top of that, your species has already put a clear nuclear stamp across the whole planet in a very short time. Atmospheric nuclear tests in the 20th century spread radionuclides worldwide. Soil, lake sediments, and ice cores all show a mid-20th century bomb spike layer. That layer contains unusual ratios of isotopes like carbon-14, as well as traces of fallout elements. In millions of years, much of the short-lived radioactivity will be gone, but the time slice marked by those tests could still show odd isotopic chemistry compared to layers above and below. If another industrial civilization had its own nuclear age, you would expect something similar. A thin layer in the stratigraphic record is where isotope ratios jump in ways normal volcanism or cosmic rays cannot fully explain. It would not be proof on its own because you've seen that rare natural reactors and other processes exist, but paired with metal anomalies, synthetic molecules and climate signals, it becomes part of a growing case. Now look at the materials built into your machines. A lot of your technology runs on alloys that do not occur naturally in bulk. Aircraft use titanium, aluminum, vanadium alloys, finely tuned for strength and low weight. Motors and wind turbines use rare earth magnets with precisely chosen ratios of neodymium, iron, boron, and other elements. Jet engines rely on high-temperature superalloys, complex mixes of nickel, cobalt, chromium, and more designed to hold together at temperatures where many rocks would soften. When these devices corrode, they do not vanish into pure dust. They break down into oxidized fragments that still retain their elemental mix. If some of those fragments are quickly buried in sediments, especially underwater or in low oxygen settings, they can persist. Give them 100 million years, and they might be transformed into odd mineral assemblages, with unusual clusters of metals that you simply do not get from magma or normal sedimentation. To a skilled geochemist, those would look like alloy fossils, mineralized leftovers of engineered materials. So now you have several classes of technosignatures in rock: unnatural metal patterns from mining and industry, nuclear isotope anomalies and vitrified layers, and alloy-derived mineral oddities. Each one alone might be explained away as natural under the right conditions. Together, concentrated in a narrow time slice, they are much harder to dismiss. Here is where the tension ramps up again. You can list many ways that a technological civilization imprints itself on a planet's crust. But you also know that natural processes can sometimes produce confusingly similar signals. Oklo looks like a reactor. End-Permian volcanism looks like a carbon nightmare. Asteroid impacts look like sudden extinction. On top of that, your sampling of rocks is incomplete and biased to easy-to-reach places. That means you're in a frustrating position. You can describe in detail what designed patterns in metals and atoms would look like. You can even see your own patterns forming right now, but you cannot guarantee you would recognize someone else's if it were subtle, local, or partly overprinted by later events. You're trying to read a planet-sized crime scene using a very small set of samples and tools that are only now getting good enough. Which leads straight into the next problem. Even if those signals exist, your main window into them, the fossil and rock record, is deeply incomplete and strongly biased. You are relying on a security camera that drops almost every frame and only records in certain rooms. How confident can you be that you have seen everything that matters? To answer that honestly, you have to look at how bad your sampling really is, and how easily a short, intense industrial phase could hide in the gaps. You probably treat the fossil record like a complete history book, but for what we're talking about, it behaves more like a glitchy security camera that only records a few random frames and throws the rest away. Start with where fossils actually come from. Most preserved remains and most good rock records come from environments that are friendly to burial, river deltas, floodplains, shallow seas, calm lake bottoms. These places collect mud and sand and they cover things quickly, and then they stay wet and low in oxygen. That's perfect for turning shells and bones into fossils and turning layers of sediment into rock. Now look at where industrial civilizations like to live. You build coastal megacities, you build along big rivers, but you also build in inland basins, plains and upland regions with good resources. A lot of that terrain is not great for long-term preservation. Upland forests, mountain valleys and many deserts barely preserve anything over millions of years. Weather, landslides and wind strip material away instead of burying it. If a civilization mostly lived on those kinds of landscapes, you would not expect a clean, continuous fossil record of its artifacts. You'd get a few scattered pieces that happen to fall into the small percentage of places that do preserve well, and everything else would be ground up or washed away. So your sampling starts biased towards certain environments and not others. But it gets worse, because your search over those environments is also extremely uneven. You've only been doing systematic paleontology for around 200 years, which is nothing compared to the age of the rocks you're studying. Most fossil digs and core studies are in richer and easier to access countries. Large parts of Africa, South America, Central Asia, Antarctica, and nearly all of the deep ocean floor are undersampled or barely touched. Think about what that means. You're trying to reconstruct the story of life, and maybe the story of civilization, by digging a relatively small number of holes in a few regions. It's like someone trying to understand modern Earth 100 million years from now by sampling a handful of sites in Europe and North America, and almost none in Asia, the Pacific, the Indian Ocean, or the deep sea floor. They'd miss entire cultures, languages, technologies, maybe entire forms of infrastructure. That is the scale of the blind spots you are dealing with right now. You can see this incompleteness in how often paleontologists are forced to update themselves. Every few years there's an announcement. This is the oldest known bird. This is the earliest snake. This is the earliest mammal relative that did X. And then, a decade later, a new fossil turns up that is older by a few million years, and the first moves back. The pattern is obvious, the record is constantly being rewritten, because new discoveries fill in previous gaps. That tells you something important about absence of evidence. When you see that a group seems to appear suddenly at a certain time, it often means you just haven't found the older material yet. The older material might exist in rocks you haven't dug into, or in rocks that are hard to access, or in places you haven't financially prioritized. So when you say we see no sign of X before this date, what you often mean is, we haven't looked enough with the right tools before this date. Now, bring this back to technosignatures and artifacts. Most fossil sites are searched with eyes and hands and sometimes basic lab tools. People look for bones, shells, teeth, big plant remains, and obvious structures in rock. They are not routinely scanning every layer at nanoscale for synthetic polymers, microplastics, or remnants of engineered alloys. They are not running high-resolution mass spectrometry on every sample to look for weird, non-biological organic molecules. They are usually not mapping trace metals at the fine detail you'd need to catch small localized industrial pollution. The kind of analysis you would need to confidently say no past industry here is heavy and expensive. It means taking existing cores and rock samples, cutting them into very thin slices, and running them through advanced instruments, looking for small but specific anomalies. Right now, you do that for a tiny subset of samples, usually when you already have a particular scientific question. That means that if an ancient industrial phase left subtle chemical fingerprints in just a few narrow layers, there's a good chance those layers have never been examined at the level required to notice. So what are the odds that you would have already stumbled on a short, ancient industrial civilization by accident? Treat fossilization and discovery as probability problems. First, the civilization has to leave behind material that can fossilize, which we already know is a low-probability process for complex structures. Second, those fossils have to end up in environments that preserve well over tens of millions of years. Third, those rocks have to stay exposed or reachable, not deeply buried or subducted. Fourth, humans have to actually drill or excavate in exactly that location. Fifth, they have to use the right level of chemical and structural analysis to recognize what they're looking at. Stack those probabilities and the chance of finding any specific short-lived phenomenon becomes small, unless that phenomenon is so globally disruptive that it leaves many redundant signals across different environments. A 10,000-year industrial civilization that arose 150 million years ago and never went fully global would be hard to see unless it seriously destabilized climate, messed with global chemistry, or spread synthetic materials everywhere. This is where the Silurian Hypothesis really sits. It is not saying we have evidence of a prior civilization and we're hiding it, and it is not saying there definitely was one. It is saying with the sampling and tools we currently have, we cannot absolutely rule out certain types of industrial phases in deep time, especially smaller, shorter ones. We can rule out a perfect clone of our modern global civilization in the last 100 million years, because we don't see its full loud footprint. But we cannot mathematically exclude all possible industrial scenarios, especially ones that are less wasteful or less global. So you're in a subtle position. You know that nature can mimic some techsignatures. You know that your tools and sampling are limited. You know that shallow, we don't see it, so it never happened arguments are not strong when the camera is this bad. That doesn't mean ancient civilization is the default answer. It means if you want to treat it seriously, you have to build a more systematic search strategy, and that leads straight to the next step. If the fossil record on your own planet is this patchy, and yet you're trying to talk about civilizations on other worlds, how do you even begin to look for industrial phases out there? How do you take what you've learned from Earth's messy archive and turn it into a test you can run on exoplanets light years away? That's where this whole idea flips outward, and your own layer in the rocks becomes a template for scanning the galaxy. You talk about alien civilizations and technosignatures, but you still haven't fully figured out how visible your own civilization really is, even on the one planet you can touch. Astrobiologists usually think forward. They ask, what signs of technology could we pick up from exoplanets? They talk about technosignatures, industrial gases in atmospheres, bright artificial lights on the night side of a planet, radio emissions, giant structures orbiting a star. The Silurian angle forces you to flip that. If your own industrial layer is hard to see in Earth's rocks after just a few million years, and maybe almost invisible after tens of millions, how realistic is it to hope you'll catch someone else's industry from 10, 50 or 100 light years away? So you turn Earth into a template. Right now, you know what a planet with an active industrial civilization looks like up close. You can see the CO2 spike, the warming, the plastic layer, the metal anomalies, the nuclear signals. You also know those signals decay, get buried, and get overwritten by tectonics and erosion. That gives you two snapshots, a live industrial planet and a fading fossilized one. The Silurian Hypothesis basically says, use those snapshots as a calibration tool. If we struggle to detect ourselves in deep time here, we need to be very modest about what we expect to see on exoplanets, especially if their industrial phase is already over. The cleanest place to look for active tech from far away is not the rock, it's the air. Future telescopes, some of them already being planned, will be able to take spectra of exoplanet atmospheres, splitting starlight that has passed through that air into different wavelengths. Each gas leaves its own pattern of absorption lines, like a barcode. You already do this for exoplanets to find water vapour, methane, carbon dioxide. Industrial societies add extra lines. Nitrogen dioxide from combustion, chlorofluorocarbons from refrigeration and industry, other complex gases that biology doesn't normally produce in large amounts. On Earth today, some of those, like CFCs, are only present at parts per trillion, but they still have clear spectral features if you look closely enough. If you ever saw a similar suite of gases on a planet 10 or 100 light-years away, at levels that are hard to explain with volcanoes or lightning or exotic chemistry, that would be a huge technosignature. But the Silurian twist kicks in again. Those gases don't last. Many industrial pollutants break down in decades to centuries. If a civilization cleans up its act, bans certain chemicals, or simply collapses, those signals fade. If the industrial phase is short and you happen to look at the planet a million years later, the atmosphere might look perfectly normal. You only get a shot at catching that spectral fingerprint while the industry is actually running, which might be a thin slice of time compared to the age of the planet. There's another lever you can pull on: energy use itself. Any advanced civilization will use power, and whatever form that power takes, it eventually turns into heat. Right now, humanity uses about 19 terawatts of power on average. That's 19 trillion watts, roughly like running around 19,000 big 1 gigawatt power plants all the time. The sun delivers on the order of 170,000 terawatts to Earth, so your current waste heat is tiny compared to sunlight. But imagine a civilization using not tens, but thousands or tens of thousands of terawatts, maybe by putting collectors in orbit or building enormous fusion infrastructure. Even if all their energy was clean, with zero greenhouse gases, the waste heat has to go somewhere. For the planet, that means more infrared radiation going into space, a kind of global fever that shows up as an excess in the thermal spectrum, beyond what you'd expect from normal greenhouse effects and starlight. From far away, with a good enough telescope, you might see a planet whose temperature pattern doesn't line up with its star's brightness, its orbit, or its atmospheric composition. That mismatch could be a clue that someone is using a lot of power. Again though, this only works while the civilization is active and large. If they scale back, collapse, or move their infrastructure off-world, the waste heat signature shrinks. Now combine this with the Silurian perspective on time. If industrial phases are short, maybe 10,000 to 100,000 years, and planets last for billions of years, then the odds that you look at a random world exactly during its high energy, high pollution, high waste heat window are not great. The galaxy could be filled with planets that had civilizations tens or hundreds of millions of years ago, left some technosignatures in their rocks, and then went quiet. From here, with light and spectra only, they look like regular planets, maybe with life, maybe even with oxygen and methane, but no obvious technology. That's the galactic Silurian problem. Even on their own worlds, ancient industrial phases might be hard to see in the geological record. For you, looking remotely, you mostly have access to the current atmosphere and maybe some rough surface properties. You cannot see buried nuclear waste or plastic horizons or alloy fossils from light years away. Those are fossil technosignatures, and they're locked under rock. You're limited to whatever is happening now, plus a bit of long-lived gas chemistry. So you fall back on the only fully known data point, Earth. Right now, this is the one planet where you can watch a civilization modify its atmosphere, climate, sediments, metals, and isotopes in real time, and then model how those signals will decay and transform over millions of years. The Silurian Hypothesis turns that into an experiment. You ask, if someone 100 million years from now studies Earth as an exoplanet, what would they actually see? If they catch us now, they see the CO2 spike, the trace pollutants, maybe some strange spectral lines. If they catch us long after we're gone, they see a roughly Earth-like atmosphere, plus a weird layer in the rocks they can't see remotely. By understanding how strong or weak our own signature is, in air, rock, and fossils, you calibrate your expectations for other worlds. You stop expecting screamingly obvious signals everywhere, and you start planning to look for smaller, more subtle mismatches. You also get a clearer idea of what it would take for a civilization to leave a truly unambiguous mark, one that survives deep time and is visible even to crude observers. And that feeds back onto us in a sharp way. If you want to be detectable as a technological species, even to your own descendants, you have to push the planet hard enough to stand out, which risks breaking the systems you depend on. If you want to be sustainable and gentle, your long-term technosignature might become faint and ambiguous. That tension becomes even more obvious when you talk about geoengineering, deliberate planetary engineering, where you start playing with climate and chemistry on purpose. Because once you start doing that, you are not just leaving accidental fingerprints, you're writing patterns into the planet, and anyone who comes after will have to decide, was this nature, or was this someone trying to steer their world? That's the next step, looking at how conscious climate control might look in the rocks, and what it says about the kinds of civilizations that make it through their dangerous high-impact phase. Right now, you're already running a global climate experiment. You just haven't been treating it like one. By burning fossil fuels, you're unintentionally geoengineering the planet, turning up the greenhouse effect and shifting temperature, rainfall, and ocean chemistry. But on top of that, people are now openly talking about deliberate planned planetary engineering, actually trying to grab the thermostat and turn it on purpose. The ideas on the table are simple to describe and terrifying to scale. One is to inject sulfate aerosols into the stratosphere, tiny particles that reflect some sunlight back into space and cool the surface. Another is ocean fertilization, dumping iron into certain regions so plankton blooms explode and pull more CO2 out of the air, then sink to the deep ocean. A more extreme concept is putting huge solar shields in orbit to cut a fraction of incoming sunlight before it ever hits the atmosphere. Each of these schemes is different in engineering terms, but they all share one fact. They change global systems in ways that should leave geochemical footprints. You already know that natural processes can do some of this. Big volcanic eruptions throw sulfur compounds high into the atmosphere, forming sulfate aerosols that cool the climate for a few years. Ice cores and sediments show these events as discrete sulfate layers, often paired with ash. If you were to deliberately inject sulfates every year or every few years, for decades or centuries to mask greenhouse warming, you would be creating a long series of those layers, not tied to obvious volcanic ash and not matching the expected timing of known eruptions. In the stratigraphic record, that would look like an extended zone with repeated sulfate pulses spaced in a regular or semi-regular way over a relatively short interval. The particle sizes and chemistry might be slightly different from typical volcanic aerosols because your industrial processes would not mirror magma perfectly. A past civilization using aerosol geoengineering for centuries could leave exactly that sort of signature. A band in the rock where the sulfate story is volcano-like in form but wrong in detail. Ocean fertilization would leave a different kind of mark. Adding iron deliberately to the surface ocean would trigger big plankton blooms in places that were previously iron-limited. When those organisms die, some of their carbon-rich bodies sink and get buried. That changes how much carbon is locked into sediments, and it also changes the balance of nutrients. In cores from these regions, you'd expect to see unusual patterns over relatively short time intervals, jumps in biogenic silica from diatoms, shifts in organic carbon content, and distinct behaviour in trace metals like iron and manganese. You'd also see changes in microfossils, tiny shells that record which species thrived and which crashed. A strong fertilization pulse might look like a bloom and bust pattern, with one set of plankton dominating for a brief period, then collapsing, followed by a different community taking over. Nature can do that too through natural nutrient surges, but a coordinated, repeated iron-adding program would impose a rhythm that might look oddly regular in the cause. On land, you're already doing your own kind of planetary engineering at the surface just by clearing forests, ploughing fields, and building cities. Deforestation and large-scale agriculture change how water flows, how soils form, and how much sediment rivers carry. Measurements today show many catchments are delivering more mud and sand to rivers because of human land use. Over thousands of years, that change builds distinct layers downstream. In those layers, a future analyst would find a strong increase in certain types of pollen from crops and weeds, and a drop in pollen from old-growth forests. They'd see more charcoal from widespread burning used to clear land or as a side effect of more frequent fires and disturbed landscapes. The clay minerals might shift because intense farming changes chemical weathering and soil formation. Urbanization adds another twist, mixing in concrete rubble, glass, brick, and metal fragments that form a pseudo-natural conglomerate. Viewed through deep time, large-scale land modification by a civilization becomes a pattern of changed erosion rates, changed sediment makeup, and changed biological signals. It's not one event, it's a sustained pressure. If an earlier industrial species covered a continent with agriculture for 20,000 years, the continent's downstream basins would carry a fingerprint, a thick package of layers that look different from what came before and after. This brings you to the core idea for separating natural climate behaviour from artificial climate control, pattern, and timing. Natural systems change, but they usually change in ways tied to orbital cycles, tectonics, or rare pulses like giant eruptions and impacts. Those have characteristic timescales, tens of thousands to millions of years for orbital shifts, bursts with long, quiet gaps for volcanoes, single spikes for impacts. A civilization, by contrast, can act on decades to centuries scales and can coordinate actions globally. So if you were looking at deep time strictly with the Silurian lens, you wouldn't just ask, do we see sulfate, or do we see blooms? You'd ask, do we see repeated, globally synchronized intervention that operate over a few hundred years, not thousands? For example, a several century band with recurrent sulfate layers not matched by known volcanic ash, at the same time as a sharp carbon isotope shift, plus weird synthetic-like molecules and odd metal patterns. The more of these signals line up within a thin slice, the less they look like slow, random nature, and the more they start to look like someone was pushing buttons. That's the real test the Silurian Hypothesis suggests. You're not just hunting for a single weird chemical or one odd fossil. You're looking for a cluster of non-natural looking patterns that switch on and off over short timescales and that match what you know an industrial species can do, both by accident and on purpose. It's the difference between a random scribble and a plotted graph. The underlying physics is the same, but one carries intention. Right now, you're at the beginning of your own potential geoengineering era. You're already running the unintentional experiment with CO2. You're debating intentional ones with aerosols and ocean iron. Whether you go ahead or not, the basic fact remains: your species is one that can, in principle, try to steer the entire planet's climate system. If someone in the distant past ever had that kind of control and used it, there should be traces, but only if you know how to read them. And that raises another uncomfortable question. What if the earlier civilization, if it existed, did not look like you at all? What if it wasn't land-based, didn't farm in the same way, didn't burn fossil fuels the same way, or didn't even live at the surface for most of its history? Would you still know how to spot it? Or are you only tuned to versions of yourself? That's where this story has to go next, into the possibility that the first industrial species on Earth might have been oceanic, buried under ice, or mostly underground, and that your entire search image for civilization might be too narrow. You keep picturing civilization as something that looks like you: cities on land, roads, cars, power plants, satellites in orbit, smokestacks, high-rises. That picture is so strong that you quietly assume If those things aren't there, then there's no civilization. But intelligence does not have to appear on dry land with lungs and hands. It can evolve in oceans, under ice, or deep in rock, and if it does, its traces might be even harder to see in deep time than yours. Start with oceans. Earth already has animals in the sea that push toward what you'd call clever. Octopuses can solve puzzles, use tools, recognize individual humans, escape tanks, and learn fast, all while breathing water and crawling over the seafloor. If evolution kept pushing traits like that for tens of millions of years, you could absolutely get an ocean-based tech species, one that never leaves the water or only does so rarely. Now, think about how such a species would build. Most of its infrastructure would be underwater. Metal frameworks anchored to the seafloor, energy harvesters on continental slopes using currents and temperature differences, high-pressure habitats in canyons 1,000 to 4,000 meters deep, roughly 3,300 to 13,000 feet. Cables and pipes running along ridges and through trenches. It might use hydrocarbons from seeps, or tap geothermal vents, or harness tides. Geologically, that is a nightmare to preserve. The deep ocean is where most sediments accumulate, but it is also where seafloor is constantly being recycled. Remember, most oceanic crust is younger than about 200 million years. Old seafloor is dragged down at subduction zones at a few centimeters per year, roughly nail growth speed, and turned into new rock. So any long-lived oceanic civilization is building and living on the part of the planet that is guaranteed to be fed back into the mantle on 100 million year timescales. Unless its structures are rapidly buried in thick sediments that later get scraped onto continents, corrosion, pressure, and subduction will erase almost everything. Even the layers you would inspect most carefully, like muddy deposits on continental slopes, are not perfect archives. They slump, they get cut by currents, they get overprinted by later events. An underwater city built 50 million years ago on a continental shelf might now be a deeply buried wedge of odd rock inside a mountain range. Or it might be gone completely. You'd only have a chance of seeing it if some of its material was trapped quickly, in a basin that had avoided subduction and stayed stable long enough to be drilled. Now, shift to ice. Picture a civilization that lives under a thick ice sheet, several kilometers thick, say 2 to 4 kilometers, around 1.2 to 2.5 miles. It could be similar to underground bases imagined for Europa or Enceladus, except here it's beneath Antarctica or some ancient ice-covered continent. It might use geothermal heat, melt channels in the ice, build habitats around subglacial lakes. Most of its structures would be in cavities carved under the ice with minimal surface footprint, maybe just some vents, outflow channels, and tiny openings. Its activity would still change the planet. Waste heat and drilling would affect how the ice flows. It could create meltwater patterns that don't match normal climate cycles. It might transport rock and minerals in unusual ways, or dump waste in specific locations, but over millions of years, ice sheets advance and retreat. Glacial ice scours bedrock, grinds mountains down, and then melts, leaving behind chaotic piles of rubble and smoothed surfaces. A lot of delicate evidence gets shredded. You might see strange erosion marks or unusual deposits of ground-up rock. But without context, they would look like weird glacial behavior, not necessarily technological. Any metal or composite structures would be crushed, oxidized, and mixed into till. Subtle chemical changes in basal sediments might survive, but you would have to sample exactly the right place and know exactly what pattern to look for. Go even deeper into the crust itself. A civilization could live primarily underground, in networks of tunnels and caverns kilometers below the surface, using geothermal heat and subsurface water. Its main energy sources could be chemical gradients, nuclear reactors, or engineered geothermal systems. It would move huge amounts of rock, create voids, and relocate minerals, all below your usual archaeological and geological search depth. Over geologic time, many of those tunnels would deform and collapse. Rock flows, fractures heal, fluids move through and deposit new minerals. You might be left with zones of unusual porosity, odd fracture networks, or strange mineralization along old tunnel paths. But again, unless you drill exactly into one of those areas and then interpret it with ancient engineering in mind, it's easy to write off as a quirk of hydrothermal activity or stress. Now consider the nature of the technology itself. Your tech stack still leaves a lot of heavy, obvious waste, plastics, metals, concrete, radioactive byproducts. But a more advanced species might transition quickly away from bulky polluting systems. It might use highly efficient closed-loop manufacturing with almost no waste. Its computing might run on materials that degrade into harmless products. Its structures could be grown from smart materials that revert to simple minerals or organics when abandoned. In that case, you'd have a civilization that leaves very little in the way of synthetic molecules, heavy metal leaks, or thick concrete slabs. It might still leave some geochemical footprint, but it would be small compared to yours. Over millions of years, with erosion, burial, and subduction, that footprint could be diluted to the point where it is nearly indistinguishable from natural variants. That creates a detection paradox. The more mature and sustainable a civilization becomes, the less damage it does to its world, and the fainter its trace in the rocks. The civilizations that are easiest to see in deep time are the messy ones, the wasteful short-lived bursts that burn fossil fuels like crazy, scatter plastics, mine metals aggressively, and maybe detonate nuclear devices. In other words, civilizations at the stage you are in now. If someone preceded you and followed a similar path, they might have had a short, loud, dirty phase early on, then either collapsed or cleaned up. If they cleaned up and moved to low-impact technology, their later history would be almost invisible geologically. You'd be left trying to spot a brief industrial spike that might have lasted only a few thousand years in rocks that are hundreds of millions of years old, with a record that is patchy and biased. So you are stuck with this uncomfortable conclusion. The version of civilization that is safest for its planet, long-term, is precisely the version that is hardest for you to detect in the deep past, and probably hardest to recognize from far away. The version that is easiest to spot, the one that reshapes atmosphere, oceans, and crust in obvious ways, is the one most likely to destroy itself or be forced to change quickly. That brings you back to the practical problem. Given all these uncertainties, biases, and weird possibilities, how would you actually design a search for ancient civilization on Earth that is honest and systematic, instead of just guessing? What specific signals would you prioritize? Where would you look? And how would you set real limits on no one was here before us? That's where this has to go next, into a concrete plan for turning the Silurian hypothesis from a thought experiment into an actual testable investigation. You want to know if anyone was here before you. You can't just stare at rocks and hope for a lucky break. You need a plan. Step 1 is simple. You build a technosignature checklist. Start with what you already know your own civilization is leaving behind. You've got plastic horizons, thin layers in sediments loaded with polymer fragments. You've got carbon isotope shifts, those negative delta -13C excursions that scream light fossil carbon was dumped into the system. You've got metal anomalies from mining and industry, weird patterns of rare earths and heavy metals. You've got nuclear isotope layers, the bomb spike style signatures and reactor byproducts, and you've got synthetic organics, PCBs, PFAS, and the rest of your chemical toolbox. Turn that into a concrete list. If a core sample shows 3 or more of those, all tightly stacked in the same narrow slice of time, you flag that interval as Silurian interesting. That's not proof of anything, but it's enough to say this layer deserves serious high-resolution analysis. You move away from vague language like, this is a bit weird, and toward a specific rule set. Multiple independent signals, compressed in time that together look like what you know technology does to a planet. The next move is obvious. You don't even need to start by drilling new holes in the seafloor. Humanity already has thousands of sediment cores and ice cores sitting in archives and freezers. Most of them were collected for basic climate and geologic work. People measured things like microfossil types, rough grain sizes, bulk chemistry, maybe a few isotopes, then stored the rest. The untouched material is still there, waiting. Modern instruments are far more powerful than what was available when many of those cores were first analysed. High-resolution mass spectrometers can detect complex molecules at parts per billion levels. Synchrotron X-ray scanners can map trace metals and mineral phases at tiny scales. You could systematically rescan existing cores, especially the parts that cross known anomaly zones, looking for the full technosignature checklist. You'd be turning old samples into new data, without touching a single fresh piece of seafloor. But you still can't look everywhere with maximum effort, so you triage. You target the suspicious time windows first. Look at intervals where you already know something big happened, but where the driver is still debated, or where the rate is uncomfortably fast. The PETM, for example. Other hypothermal events with sharp warming and carbon spikes. Odd local warming spikes in particular basins. Abrupt extinctions that don't have a clean asteroid or flood basalt explanation. Those are natural places to ask, is there any collateral evidence of industry hiding in here? In practical terms, that means taking cores that span those events and scanning right across the anomaly. You look not just at carbon and oxygen isotopes, but also at trace metals, weird organics, sulfur patterns, and any signs of synthetic-like materials. You check whether the timing of different signals lines up tightly, or whether they're spread out in ways that scream slow geology. If you see multiple technosignature-style clues stack up at the edge of one of these events, you push harder. If you see clean volcanic-looking patterns with no extra anomalies, you mark that as strong evidence for a purely natural cause. Doing this seriously is not a one-discipline job. It's not just paleontology or just geochemistry, it's full-on forensics across several fields. You need climate physics to model what different carbon and heat pulses would look like. You need organic chemistry to distinguish natural complex molecules from potential synthetic analogues. You need nuclear physics to read subtle isotope patterns. And you need computer science because the data volume is enormous. Think about how SETI searches radio noise for structured patterns. Here you do the same, but with stratigraphic data. Machine learning systems could chew through terabytes of measurements from cores and outcrops, looking for non-random alignments, for layers where carbon shifts, metals spike, and odd organics all appear within a few millimeters of each other. Humans are good at spotting simple patterns, but not at holding tens of thousands of variables in mind at once. Algorithms can flag candidate intervals. Humans can then go back and attack those with targeted lab work. Now say you do all of that over decades. You build the checklist, rescan cores, focus on suspicious windows, run the pattern searches, and in the end you don't find anything that holds up. What do you actually gain? You gain something very important: limits. You can say with increasing confidence that in the last, say, 100 million years, there has probably not been a global-scale industrial civilization on Earth that looked like ours in key ways. No one burned fossil carbon at our level, over similar timescales across the whole planet. No one mined and moved metals at anything like our scale. No one filled the oceans with synthetic polymers and persistent organics in a way that reaches every basin. That doesn't prove that no intelligence ever arose. It doesn't exclude smaller, more local tech phases, or very clean, low-impact ones, or very ancient ones that got tectonically erased. But it does squeeze the parameter space. Any prior civilization would have to be less global, less resource-intensive, shorter in duration, more constrained, or much deeper in time than that 100 million year window. You move from no evidence, in a vague sense, to quantified boundaries on how big and messy any pre-human tech could have been. And that's where the emotional weight really hits. Because once you start putting upper limits on past civilizations, you also start framing your own. You're actively choosing right now how loud your layer will be and how future scientists, human or not, will classify you in their models. So the next question becomes unavoidable. If you're not the first, what does that say about how often civilization happens? And if you are the first, what does that say about how easy it is to destroy the only one you've got? Here's the uncomfortable possibility: you might not be special at all. If industrial civilizations can happen more than once on the same planet, then intelligence and technology are not one-off accidents. They're phase transitions. They're what a complex biosphere does when you give it enough time, energy, and stability. First you get single cells, then multicellular life, then big animals, and every now and then you cross a threshold where one species figures out how to turn stored energy into industry. If that's true, then Earth is not a freak. It's a standard lab run. The sequence becomes long ages of biology, then a brief burst of industry, then a crash or a transition, then recovery, maybe a new form of life taking over. The universe could be full of planets that have gone through multiple cycles like that, with different species, different technologies, but the same basic pattern. You're not playing a unique game, you're just taking your turn. That immediately hits the classic question, where is everybody? The Fermi paradox sounds sharp when you phrase it as, if intelligent life is common, why don't we see any? But the Silurian perspective changes the timeline. The key question becomes, where is everybody right now? If technological phases are short, say 10,000 to 100,000 years, against planets that last for billions, the odds that two neighbours in the same patch of galaxy are both in their industrial window at the same time are low. You're talking about tiny slices of time scattered over huge spans. Most of the time, a given world is either pre-industrial, recovering from some crash, or long past its tech burst with only subtle fossils of that period left. So the galaxy could be full of used planets, worlds that had civilizations millions or hundreds of millions of years ago, built their own versions of cities and power grids, altered their climates, maybe wrecked themselves, maybe moved on, and now look quiet again. When you point a telescope at them, you're seeing them in between waves. No bright radio chatter, no obvious megastructures, just a normal-looking atmosphere and surface. The fact that you don't see active, loud civilizations everywhere doesn't mean they never existed. It might just mean you're late to some parties and early to others. Now bring this back home. If someone came before you on Earth and vanished, their story becomes an existential precedent. It's not just an interesting detail, it's a warning carved into the background of your own life. Maybe they hit a hard resource ceiling, burned through their easiest energy sources, and couldn't transition in time. Maybe they drove their climate past a tipping point, triggering feedbacks they couldn't control. Maybe they fought, and their weapons were bad enough to leave geochemical scars that you can still detect if you look closely. Events like the PETM and the end-Permian extinction show how fast warming and environmental stress can get deadly, even without technology. In those cases, you're probably looking at natural drivers, volcanism and carbon release. But the physics is the same either way. Once you push the system hard enough, oceans lose oxygen, temperatures spike, ecosystems snap. The timescales can be much shorter than the comfortable slow change picture you might prefer. You don't have to run industry for 10 million years to break things. You can do it in tens of thousands, possibly less, if you mismanage feedbacks. Layer a prior civilization on top of that. Their collapse, if it happened, would be geological proof that intelligent doesn't automatically mean long-lived. That's a brutal data point for your own future. It says even if evolution can make tech over and over, there's no guarantee any given run lasts long enough to escape its own planet, or to grow into something stable. Here's another flip that should bother you. From the perspective of any future intelligence on Earth, we are the hypothetical ancient aliens. Picture a species 100 million years from now, digging into what used to be New York, Mumbai, Lagos, Shanghai. They find a layer just a few centimeters thick, loaded with odd chemistry, plastic-derived carbon, weird metal ratios, a spike in extinctions, and some strange fossil mammals, maybe including the descendants of rats and raccoons that adapted to your cities. To them, we're the Silurians, the rumoured first civilization. They argue in their conferences and their comment sections about whether the anomalies in that layer are enough to say industrial civilization, or whether it's just an extreme natural event. Some say yes, some say no, some build careers on the debate. You are the maybe civilization they're fighting over. Once you view yourself that way, your timeline stretches. Your actions today stop being only about the next election, the next 10 years of GDP, or the next tech cycle. They become part of what the rocks will say about you to minds that might not exist for tens of millions of years. Sustainability stops being a polite word for less pollution now, and turns into a blunt question: what kind of geologic event do you want to be? Do you want to be a sharp, ugly spike, a brief, high-intensity pulse of carbon, plastics and extinction that looks, in hindsight, like a planetary accident? Or do you try to flatten that spike to stretch your presence out, to reduce the violence of your impact so that your layer blends more gently into Earth's long story? One path makes you obvious but short-lived, the other makes you less visible but potentially far more enduring. That is the real weight of the Silurian Hypothesis. It's not about proving ancient lizard engineers, it's about forcing you to ask where civilization fits in the life cycle of a planet, and whether intelligence usually survives its own power or burns out and gets replaced. You don't have a full answer yet, but you are generating the data your descendants, or someone else's, will use, which brings everything back to you right now in this an active slice of time. You are in the process of writing the very layer future scientists will drill through and argue about. You are deciding how loud your signal is, how long it lasts, and what conclusions someone millions of years from now will draw about what kind of species you were. The final step is accepting that this isn't theoretical anymore. You're literally writing the Silurian Hypothesis into the rocks as you live. Right now, you're not just living in history, you're writing a physical line in the planet itself. Every kilometre you drive, every flight you take, every watt you pull from a power grid, every kilogram of plastic you trash or recycle, all of that is changing what the early 21st century looks like in the rock record. Sediment is falling onto seafloors and lake bottoms right now, a few millimetres every 1,000 years. In that material there are microplastics, industrial soot, heavy metals, fertiliser runoff, odd isotopes, and the remains of the species you're pushing toward extinction. Fast forward tens of millions of years, that messy surface layer is buried, compacted, heated a bit, but not enough to erase it. It becomes a slice of rock a few centimetres thick, maybe 2 to 10 centimetres, around 1 to 4 inches, sandwiched between older, more normal layers. Inside that slice, future scientists can pick up a signal. Sharp carbon spike, rapid warming, plastic-derived organics, weird alloys, nuclear traces, and a sudden shift in fossils. That's your layer. That's your one physical sentence in Earth's deep time story. Here's the part no one voted on. Humanity is already running a planetary scale experiment in detectability. You're testing how obvious an industrial civilization is in geology, climate, and chemistry just by doing what you're doing every day. You didn't sign a consent form for that. There was no global agreement that said, yes, let's find out how loudly we can engrave ourselves into the crust. But the test is happening anyway. At some point in the far future, geologists, whether human descendants, something that evolved after you, or visitors from somewhere else, will drill into that interval. They will be able to answer the Silurian Hypothesis for you. They'll see either a sharp, unmistakable industrial fingerprint, or a fuzzier pattern that's hard to interpret. Right now, with rising CO2, spreading plastics, and accelerating extinction, the needle is swinging toward loud. You're on track to leave a very clear, very violent spike. This loops the whole question back onto you. Could there have been a civilization before us? Sounds like a question about dinosaurs with machines or lost empires, but underneath it's a mirror aimed at your own face. What actually makes you different from all the other species that have come and gone, and how long can that difference last before the planet pushes back? You already know one piece of the answer. Biology is tough. Life has bounced back from asteroid impacts, supervolcanoes, and massive climate swings. It doesn't come back with the same species, but it comes back. Complex ecosystems rebuild on 100,000-year to million-year timescales. What you do not know is whether technological intelligence is tough in the same way, or fragile. Does it usually manage to stabilize and spread? Or does it tend to burn itself out and vanish after a short burst of power? Either way, you don't get to escape leaving a trace. There is no option where your civilization leaves nothing in the rocks. The only real choice is what kind of trace you leave. One option is a short, violent spike. CO2 shoots up, temperatures jump, extinction rates surge, synthetic chemicals peak, then everything crashes. In the core, that looks like an abrupt, ugly glitch. The kind of layer future students look at and say, something went very wrong here. The other option is a longer, quieter presence. You still alter things. You can't run industry and technology at scale without touching the system, but you pull back from the cliff. You decarbonize energy, cut waste, design materials that don't spread everywhere, protect ecosystems instead of strip mining them, and run your tech on closed loops. In rock, that looks like a smoother transition. There is still a technosignature, but it's lower intensity and spread over a longer time. It says, this species figured out how to live with its world, not just on it. There's a tension here you can't avoid. The more dramatic and short-lived your burst, the easier it is for the rocks to record it. Clear spike, heavy impact, obvious lesson. The more you stabilize, the more your signal blends into natural variability. From a purely be-remembered standpoint, the reckless path is easier. From a still-be-around standpoint, the reckless path is suicidal. So when you ask, did another civilization come before us? You're actually poking at a bigger question. Are you at the beginning of a pattern the universe repeats over and over? Biosphere, tech, crisis, recovery, new species? Or are you an outlier? A one-off run that either makes it through this bottleneck or doesn't? Are you the first run on this planet, with no precedent and no second chance, or just the latest in a line you haven't found yet? The rocks don't answer that yet. Right now, they're still being written. Sediment is falling, corals are dying, forests are being cut, cities are rising, and your industry is imprinting itself in carbon, metals, and molecules. Somewhere far in the future, someone will read that layer and file you in their mental categories. Maybe they'll say, this was the first civilization on Earth, the one that proved tech could exist here at all. Maybe they'll say, here's another one, just one more brief industrial phase between longer stretches of ordinary biology. Those are the two headings you're drifting toward even if no one writes them down. The first, or just one more. Right now, you're still choosing which one they use. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect, like the video, and subscribe to the channel for more such amazing videos.